Dear students, today we will discuss continuity and differentiability. Calculus is one of the major branches of mathematics. That calculus is divided into two parts, differential calculus and the integral calculus. Today that we are going to study continuity and differentiability. It is from differential calculus. Differential calculus includes limits, which you have already studied in your first PUC, continuity, differentiability, derivatives, some part of it we have studied already, and the applications of derivatives. Okay. So, the first chapter here in differential calculus is continuity and differentiability. To understand continuity, one must know what are limits. So, before we go to continuity, let us first discuss some of the things which we have already studied about limits. Limit of a function. Let f of x be any function. Then we say that limit of f of x as x approaches a, this is equal to L, some L, provided this f of x approaches L whenever x approaches A, be it from the left side or be it from the right side. Let me give you an example. Suppose if I take f of x is equal to x square minus 9 divided by x minus 3. X square minus 9 divided by x minus 3. Here, if I ask you to find out what is f of 3, the answer is does not exist. F of 3 does not exist. Why it does not exist? Because the domain of this function is the set of all real numbers except 3. Because when we put x equal to 3, this denominator becomes 0. So, the domain of f of x is set of all real numbers except 3. Okay. So now this is the function I have considered. I want to find out, I want to check whether this function has a limit or not at x equal to 3. We already know that at x equal to 3 the function is not defined. But let us check whether the limit exists or not. So limit exists. To check whether the limit exists or not, we need to find out what is left hand limit and what is right hand limit. Left hand limit is nothing but limit of x tends to 3 minus f of x. That means when x approaches 3 from left side. I would like to draw the graph of this function. At x equal to 0, the value is 3. Because if I put x equal to 0 here, I am getting minus 9 divided by minus 3, which is equal to 3. Then at x equal to 1, if I put x equal to 1, this will become 1 minus 9, that is minus 8 divided by minus 2, which is equal to 4. Let us say this is 1, 2, 3, 4, etc. So at x equal to 1, it is 4. Then at x equal to 2, it is 5. At x equal to 3, it is not defined. At x equal to 4, it becomes, what happens at x equal to 4? 16 minus 9, 7 divided by 4 minus 3, which is equal to 1. So at x equal to 3, it is not defined. At x equal to 4, it will become 7. So the graph looks like this. This is a straight line. Here it looks in this way, but there is a gap at x equal to 3. At x equal to 3, there is a gap in the function. As you can observe here, there is a gap here at x equal to 3. So that is because the function is not defined at x equal to 3. Oh, now let us try to find the left hand limit and the right hand for this function f of x as x approaches 3. Okay. So as x approaches 3, first I would like to find the left hand limit. When x approaches 3 from left side, this f of x is approaching. So what is the value of this? As x approaches 3 from left side, this, see, this is 4, 5 and 6. This is your x-axis, sorry, y-axis. See, at x equal to 3, when x approaches 3 from left side, f of x approaches 6. And on the other hand, when x approaches 3 from right side, f of x, there also f of x approaches 6. So, limit x tends to 3 minus f of x is equal to, limit x tends to 3 minus f of x and replaced by x square minus 9 divided by x minus 3. That's equal to 6. Right hand limit is equal to limit x tends to 3 plus f of x. That's equal to limit x tends to 3 plus x square minus 9 divided by x minus 3, which is also equal to 6. So as you can observe, left hand limit is equal to right hand limit. Therefore, we say limit exists and we write limit of f of x as x approaches 3 is equal to 6. Okay. So limit exists here. Then let me take another example. Limit x tends to 0 mod x, modulus of x. This is a well-known function. I want to check what happens to mod x as x approaches 0, whether this limit exists or not. That we shall test. So mod x, according to definition, mod x is equal to x if x is greater than or equal to 0 and minus x if x is less than 0. Mod x over x if x greater than or equal to 0 and minus x if x is less than 0. Okay, so what it suggests is that whenever x is negative, this function is defined as minus x, and whenever x is positive, it is defined as x. The graph is also very well known to you. This is the graph of modulus of x. Set to 0. Now we are testing at 0 what happens to limit of f of x. Okay. So first I would like to find out left hand limit. Left hand limit is equal to limit x tends to 0 minus f of x. F of x is mod x, right? That's equal to limit x tends to 0 mod x. So when I write x tends to 0 minus, it indicates that x is approaching 0 from left side. So when x is approaching 0 from left side, means x is less than 0. When x is less than 0, the function is defined as minus x. So limit x tends to 0 minus x is equal to 0. Then if I take right hand limit, that's equal to limit x tends to 0 plus f of x. F of x is mod x here. X tends to 0 plus. Its meaning is that x is approaching 0 from right side. In other words, x is very close to 0 but greater than 0. So here we are talking about x in this interval. X is approaching 0 from right side, which means when x approaches 0 from right side, its meaning is that x is positive. Whenever x is positive, mod x, we will take it as plus x. So now limit x tends to 0x is equal to 0. So left hand limit is equal to right hand limit. Hence the limit exists. Therefore, I can write limit x tends to 0 mod x is equal to 0. Okay. Let me take one more example on limits before we discuss what are continuous functions. Okay. Another well-known example I would like to take. I would like to take step x, and I want this limit x tends to 2 step x. Step x or the greatest integer function. Step x means the greatest integer less than or equal to x. So I would like to draw the graph of this function. This greatest integer function is also known as unit step function. Okay, this is 0, 1. From 0 to 1 it is defined as 0. At 1 it is 1. From 1 to 2 it is 1. At 2 it is 2. So this is the graph of step x. Okay. Now I want to find out that limit extends to 2 step x. First I will take left hand limit. Left hand limit is equal to limit extends to 2 minus step x. Extends to 2 minus step x means x is approaching 2 from left side. When x approaches 2 from left side, that means x is very close to 2 but less than 2. In other words, x may take the values 1.9, 1.95, 1.99, 1.99999, etc. So at all those points, step x value will be equal to 1. That is, x is very close to 2 but less than 2. There, step x will be equal to 1. On the other hand, if you find out right hand limit, this is equal to limit extends to 2 plus step x. Here x is approaching 2 from right side. X is approaching 2 from right side means x is very close to 2 but greater than 2. So x may take the values 2.1, 2.05, 2.001, 2.00001, etc. At all those points, step x value will be equal to 2. So as you observe now, left hand limit is 1 and right hand limit is 2. Hence, the limit does not exist. Okay. So now, these are some basic definition of limits, and we have seen several properties of limits. Okay. Now, let me discuss continuous functions or continuity at a point. Okay. So, let us say this is the graph of certain function, say y equal to f of x. I can draw this graph without lifting the pen. Okay? Then this is a continuous function. Whereas, if we look at our previous example again, this, as you know, it's a very well-known function, is the graph of step x. Here, we cannot draw the graph of this function without lifting the pen. Okay? So, this is a discontinuous function. This is not continuous because I cannot draw it. As the word itself suggests, there are some breaks here. At every integer, there is a break. So, we cannot draw the graph of this function without lifting the pen. Therefore, this is a discontinuous function. Whereas, this graph can be drawn without lifting the pen. Therefore, this is a continuous function. Okay. However, this is not a mathematical definition. If you write this definition in the example, certainly you are not going to get any marks other than 0. Well, so what is the exact definition of continuous function? This is basically how you understand what are continuous functions. Now I will give you what is the definition of continuous function. Okay. First we shall discuss continuity at a point. Let y is equal to f of x be any function, any real function. When I say any real function means its domain is either the set of all real numbers or any subset of it. Let a be any point in its domain. Let a be any point in the domain of f of x. Then we say that the function f of x is continuous at x equal to a. We say that the function f of x is continuous at x equal to a if limit extends to a f of x is equal to f of a. If this happens, that is, limit of a function exists as x approaches a, if limit exists and if it is equal to f of a. It is equal to f of a means the value of the function at x equal to a if they are equal. So when I say this limit exists means, as we already know, left hand limit must exist, right hand limit must exist, and they should be equal. So then only we can say this limit exists. And in addition to that, it should also be equal to the functional value. Function value means the value of the function f of x at x equal to a. If that happens, then we say that the function is continuous at x equal to a. Okay. So now let us look at the previous examples only, what we discussed earlier. Initially I took f of x is equal to x square minus 9 divided by x minus 3. And at 3, let us see whether this function is continuous or not. We saw that limit extends to 3 f of x. This exists. So, and this is equal to 6. Limit exists and the value of the limit is equal to 6. But what about f of 3? In other words, what about the functional value? Its meaning is the value of f of x at x equal to 3. F of 3 does not exist. Does not exist. Okay? Because domain is a set of all reals except 3. Right? Here, though limit exists, but that is not equal to the functional value. Functional value does not exist. Hence, this is not a continuous function. Now, I'll go back to that graph. So, there was a break at 3. Right? So, you just recall that. So, at 3, there is a break. So, the function is discontinuous at x equal to 3. Now, let us look at the next example. The next example what we discussed was f of x is equal to mod x at x equal to 0. So, f of x equal to mod x at x equal to 0. Say, now we saw that limit extends to 0 f of x is equal to 0. Right? We already discussed that. The left hand limit is 0, right hand limit is also 0. Now f of 0, what is f of 0? F of 0 is also equal to 0. So limit exists which is equal to 0 and the function is defined at 0, its value is also equal to 0. So this function is continuous at x equal to 0. So then one more example what we discussed was this step x at x equal to 2. So there we saw limit itself does not exist. If limit itself does not exist, then there is no question of it being continuous. It can never be continuous. So by looking at all this, what we can come to one conclusion about continuity is that for a function to be continuous at a particular point, left hand limit should exist, right hand limit should exist. The functional value, function should be defined at that point and all those three should be equal. Left hand limit is equal to right hand limit is equal to the functional value. Then we can say that the function is continuous at that particular point. Okay, let us look at some more examples. I will say let f of x is equal to 2x plus 3 if x is less than or equal to 1 and 3x minus 2 if x is greater than 1. I want to know what happens to this function at x equal to 1. At x equal to 1, whether this function is continuous or not, that we need to check. Okay. So, first we will find out left hand limit. Limit extends to 1 minus f of x. That's equal to limit extends to 1. When I write that limit extends to 1 minus f of x, don't think that x is approaching minus 1. It is not. Its meaning is x is approaching 1 from left side. So whenever x approaches 1 from left side, means x is less than 1. So when x is less than 1, the function is defined as 2x plus 3. Okay, whenever x is less than 1, it is defined as 2x plus 3. So here, if I apply the limit now, put x equal 1 here directly, 2 plus 3, which will give you 5. Then right hand limit, that's equal to limit x tends to 1 plus f of x. X is approaching 1 from right side. When x approaches 1 from right side, its meaning is that x is very close to 1 but greater than 1. Whenever x is greater than 1, which is defined as 3x minus 2. Now here if you put x equal 1, we are going to get 3 minus 2, which is equal to 1. So observe, left hand limit is 5 and right hand limit is 1. So limit does not exist, hence it cannot be continuous. For it to become continuous, left hand limit must be equal to right hand limit, must be equal to the value of the function at that point. Okay. So now this point, at this point the function is discontinuous. We say if a function is not continuous at that point, then we call that point as a point of discontinuity. That function is discontinuous at that particular point. So far what we discussed is the continuity of a function at a particular point. Now, in order to say that a function is continuous in its domain, the function is continuous in its domain, then it should be continuous at each and every point in its domain. A function, if it is continuous at each and every point in its domain, then we can say that the function is a continuous function. The best example is sin x. If you take f of x equal to sin x, the domain is set of all real numbers. Look at the graph of this function. You can draw the graph of this function without lifting the pen. Although I have lifted here once, but you can draw the graph of sin x without lifting the pen, and you don't see any break anywhere in this function. So this is an example for a continuous function. Okay. Then see, I told you that step x at x equal to 2 is discontinuous because at 2 limit itself does not exist, therefore it is discontinuous. However, see, at integers it is discontinuous, but if I take any non-integral point, say I want to test the continuity at x equal to 2.5, let us just go back to the graph of step x. From 0 to 1 it is 0, from 1 to 2 it is 2, from 2 to 3 it is, from 1 to 2 it is 1, and from 2 to 3 it is 2. So here is our 2.5. We want to check whether the function is continuous or not at this particular point. So now what do I do? Limit, left hand limit I find out, which is equal to limit x tends to 2.5 minus, which meaning is x is approaching 2.5 from left side. That is equal to, when x approaches 2.5 from left side, means x is very close to 2.5 but less than 2.5. Say somewhere in the region of 2.4, 2.45, 2.48, 2.49, 2.49999, etc. At all those points, step x value will be equal to 2 itself. So limit x tends to 2.5 from left side, step x, this is equal to 2. On the other hand, right hand limit, that's equal to limit x tends to 2.5 plus. When we write x tends to 2.5 plus, its meaning is that x is very close to 2.5 but greater than 2.5. X is approaching 2.5 from right side. So its meaning is x may take the value somewhere around 2.6, 2.55, 2.51, 2.5001, also equal to 2. As you observe here, left hand limit is 2, right hand limit is 2, and the function value is also equal to 2. So the function is continuous at x equal to 2.5. Okay. So from this, what we can conclude is that step x is discontinuous at all integers and it is continuous at all non-integers. So in other words, on the set of integers, on z it is continuous and on r minus z it is on z it is discontinuous and on r minus z it is a continuous function. Okay. Now let us look at some problems on continuity of a function. The question is, examine the continuity of the following functions. Examine the continuity of the following functions at the specified point. So they give you one function and they also give you one point. We need to check whether the function is continuous at that point or not. First problem, f of x equal to 5x minus 2 at x equal to 3. This is the question. We need to check whether this is continuous or not at x equal to 3. So for that, I would like to find out the limit of f of x as x approaches 3. See, now for this particular problem, there is no need to go for left hand limit and right hand limit, because to the left side of 3 and to the right side of 3, function is defined as 5x minus 2 only. So we can directly write limit extends to 3, 5x minus 2. Directly apply the limit, find 315 minus 2, which is equal to 30. This is the limiting value. Limit of f of x as x approaches 3, which is equal to 13. Then f of 3. What is f of 3? Put x equal to 3 here. Find 315 minus 2, which is equal to 30. So limit from this we can say limit of f of x as x approaches 3 is equal to f of 3. Therefore, f of x is continuous at x equal to 3. Okay? Then let us look at the next problem. Question is same. We need to check the continuity of the function at the given point. F of x is equal to, so the function is defined like this, x square minus 16 divided by x minus 4 when x not equal to 4, and it is defined as 10 when x is equal to 4 at x equal to 4. Okay. So here we want to check the continuity of the function at the point x is equal to 4. We have the function f of x, which is defined as x square minus 16 by x minus 4 whenever x is not equal to 4, and it is defined as 10 whenever x is equal to 4. Okay. So now let us find out limit extends to 4 f of x. Okay. For this problem also, there is no need to find out left hand and the right hand limit separately. Now you may be thinking, sir, why it is so? In some earlier cases, you had found out left hand limit and right hand limit separately, and now why you are not finding? That may be one of your questions. Why we did not find out separately is because, see, just understand how this function is defined. Say, let me draw here. then this is x y axis, these are x axis. So this is 4. See what they have said, when x is not equal to 4, the function is defined as x square minus 16 by x minus 4. And at x equal to 4, it is defined as 10. So at x equal to 4, it is defined as 10 somewhere here. Okay. And whenever x is not equal to 4, say in this region, and also in this region, the function is defined as x square minus 16 divided by x minus 4. To the left side of 4 and to the right side of 4, f of x is defined in the same way. Hence, there is no need to find out the left hand limit and the right hand limit separately. Okay, so I directly go for this. Limit x tends to 4, x square minus 16 divided by x minus 4. Already we have studied enough about limits to solve this problem. We can either write this 16 as 4 square and then use the formula limit x tends to a, x power n minus a power n divided by x minus a is equal to m into a power n minus 1. That formula can be used, or else you can factorize this, write x square minus 16 as x minus 4 into x plus 4 divided by x minus 4. We have x minus 4 gets cancelled, hence you have limit x tends to 4, x plus 4. Apply the limit, we get 4 plus 4 which is equal to 8. Okay. So from this we see that limit x tends to 4 f of x is equal to 8. And what about f of 4? F of 4 means the value of the function at x equal to 4. The value of the function at x equal to 4 is equal to 10. So we observe that limiting value, limit of the function as x approaches 4 is equal to 8, whereas the functional value is equal to 10. They are not equal. Limit of the function is not equal to the function value, therefore this function is discontinuous at x equal to 4. Okay, let's move to the next question. F of x is equal to 3x minus 1 if x is greater than or equal to 0 but less than 1, and 4 when x is equal to 1, and 2x plus 5 whenever x is greater than 1. Oh. See, at x equal to 1. We are asked to find the test the continuity at x equal to 1. We have to examine the continuity at x is equal to 1. Let's see how this function is defined. So whenever x is between 0 and 1, then x is greater than or equal to 0, less than 1, the function is defined as 3x minus 1. At 1, it is defined as 4. When x is greater than 1, it is defined as 2x plus 5. Students, for this particular problem, while finding the limit, we need to go for left hand limit and right hand limit separately. Why it is so? Let me do it again. Let me draw this. See here, this is 1. At x equal to 1, it is defined as 4. Let us say 4 is there. It is defined as 4 at x equal to 1. To the left side of 1, from x greater than or equal to 0 to less than 1, in this region, it is defined as 3x minus 1. Then whenever x is greater than 1, there it is defined as 2x plus 5. Okay? To the left side of 1 and to the right side of 1, f of x is defined in two different ways. Hence, we need to go for left hand limit and the right hand limit separately in this particular problem. Okay. So left hand limit I would like to find out. That's equal to limit x tends to 1 minus f of x. So when I say 1 minus f of x, its meaning is, as I have already mentioned, x is approaching 1 from left side. That means x is close to 1 but less than 1. close to 1 but less than 1. Less than 1, so I should take 3x minus 1. So limit of 3x minus 1 as x approaches 1, put x equal to 1 here. Put x in 1 here, 3 minus 1, we get 2. Then right hand, that's equal to limit x tends to 1 plus f of x. That's equal to limit x tends to 1. X is approaching 1 from right side, that will give you 2x plus 5. That's equal to, put x to 1 here, 2 plus 5, that will give you 7. Left hand limit is 2, right hand limit is 7. So limit does not exist. The functional value is equal to 4. None of them are equal. So limit itself does not exist. Hence, the function is discontinuous at x equal to 1. Okay. Let us look at the next question. Question is saying we have to test the continuity of the given function at a given point. Okay. The function is f of x is equal to 2x plus 1 whenever x is less than 3. And 7 when x is equal to 3. And it is 3x minus 2 when x is greater than 3 at x equal to 3. Okay. We are asked to find the examine the continuity of the function f of x at x equal to 3. So whenever x is less than 3, the function is defined as 2x plus 1. At x equal to 3, it is defined as 7. When x is greater than 3, it is defined as 3x minus 2. Okay. So now, here obviously we have to go for left hand limit and right hand limit separately. I don't think it requires the explanation again. So left hand limit I find out, that's equal to limit x tends to 3 minus f of x. That is, x is approaching 3 from left side. When x approaches 3 from left side, that means when x is less than 3, the function is defined as 2x plus 1. That's equal to, now if you apply the limit here, 2 into 3 is 6 plus 1 7. Then right hand limit is equal to limit x tends to 3 plus f of x. That's equal to limit x tends to 3. X approaches 3 from right side, it is defined as 3x minus 2. 9 minus 2, 7. So left hand limit is 7, right hand limit is 7. Hence the limit exists, hence the limiting value. Limit x tends to 3, f of x is equal to 7. The functional value, f of 3. What is f of 3? That means, what is the value of the function at x equal to 3? At x equal to 3, it is defined as 7. So as we observe here, limit of f of x as x approaches 3 is equal to 7. And f of 3 is also equal to 7. So limiting value is equal to the functional value. Hence, f of x is continuous at x equal to 3. Okay? Is that clear? Okay, students. We will discuss some more problems in the